Okay, as I promised, I'm going to talk about the equations that describe rotational motion when the acceleration, the angular acceleration is constant. So let's go back to our definition. Alpha is our angular acceleration. It's d omega dt, and we're going to say that it's a constant value. So we're going to do something that we basically have done before, but with linear quantities. We're going to start with this assumption that alpha is a constant. So I'm just going to use the symbol alpha, and we'll just think of it that it's some number. We don't know what it is. It depends on our problem. I'm going to integrate this expression to get an expression for how omega depends on time in this scenario, and then also integrate it one more time to figure out what theta will look like and how it depends on time. And then finally, we're going to eliminate time and come up with an expression that is going to relate alpha, omega, and theta. So let's keep all that straight. All right, so we've done this before, but we did it for linear quantities. I'm going to do what math people like to call separation of variables. We can use that term too. So I'm just rearranging this. Honestly, this is a differential equation, but it's super simple, and it's something that you have the capability of solving. Absolutely. So I have alpha dt on one side and d omega on the other. Remember, alpha is a constant, so that's okay. It's like having 3 times dt. So the dt and the d omega tell me the variable I'm going to integrate over. So on the left-hand side, I'm going to integrate time from 0 to some time t. And our limits for omega have to match up with our limits for time. So the omega when t was 0, we usually call omega naught. And then the omega at some arbitrary time, we just call omega. So I integrate the left-hand side. Really all I'm doing is integrating dt. And so I get alpha times t, evaluated at 0 and t. The right-hand side is similar in its simplicity. I just get omega, evaluated at omega naught, and omega. So this ends up, the left-hand side gives me alpha t. The right-hand side will give me omega minus omega naught. I'm going to rearrange it, and I get omega equals omega naught plus alpha t. That is my first equation that I want to remember. This tells me how velocity, angular velocity depends on time when the angular acceleration is constant. Now we're going to work with omega, which is equal to d theta dt is equal to omega, is equal to omega naught plus alpha t. And so we're going to integrate that. I'm going to multiply both sides through by dt. And so the left-hand side, I'm going to integrate over theta. The right-hand side, I'm going to integrate over dt. I go from 0 to t. This will have to go from theta naught to theta. Again, keeping in mind that the limits have to match on both sides. When I integrate d theta, I just get theta. It's going to be evaluated at theta naught, theta. On the right-hand side, it's going to be a little bit more complicated this time. I'm going to get omega naught times t plus 1/2 alpha t squared, evaluated at 0 and t. When I put in the limits of my integration, I get theta minus theta naught is equal to omega naught t plus 1/2 alpha t squared. So theta is equal to theta naught plus omega naught t plus 1/2 alpha t squared. That is my next expression that I want to remember. Oh, my pens are so noisy. Okay, I'll have to make a note of that. Don't use these pens, they're annoying. Okay, I'm going to do one last expression before we stop. And I want to show you how we can come up with an expression that relates omega, alpha, and theta, but eliminates the time. And we're going to start with this expression one more time. So alpha was equal to d omega dt, but I'm going to change that derivative by using what we call the chain rule. And I actually did do this in class, I think, when I did the work kinetic energy theorem. So instead of having d theta dt, d omega dt, sorry, I have d omega d theta dt. So the idea is that if I multiply those two derivatives next to each other, I end up with d omega dt. But the nice thing is this is going to allow me to eliminate time, because I have d omega dt, d theta, but d theta dt is just omega. So I've actually gotten rid of the explicit time dependence here. So then I have alpha times d theta is equal to omega times d omega. I'm going to integrate from omega naught to omega, integrate from theta naught to theta. So you can see I'm going to not have any time in this. On the left-hand side, I'm going to end up with alpha times theta minus theta naught. And on the right-hand side, I'm going to end up with 1/2 omega squared minus 1/2 omega naught squared. Now, I'm going to rearrange this a little, and again, I think it'll look somewhat familiar. I end up with omega squared is equal to omega naught squared plus 2 alpha theta minus theta naught. And that becomes the third equation that I want to remember. Now, my claim was that these equations should look familiar to you when we think about linear quantities, and so in the next video, I'm going to show you how we can see that they're very, very similar.